Welcome to the Rani Chennamma University BSc 4th Sem Physics. Here we are going to study the Unit 1 Interference. Session 2, it consists of the theory of interference due to Fresnel's biprism and determination of wavelength of monochromatic light. The learning objective of this session is to understand the theory of Fresnel biprism and also use to determine the wavelength of monochromatic light. So we need some prerequisites for this, that is the conditions for constructive and destructive interference and its path difference, and also the construction and working of Fresnel biprism. Here in the session 1 we have studied the interference as it is the phenomena of a modification in the intensity of a light due to the distribution of a light energy in the region of a superposition of two or more light waves. So we get bright and dark fringes. Bright fringe is due to a constructive interference and dark fringe is due to a destructive interference. And for a constructive interference, the path difference equal to n lambda. And for a destructive interference, it is path difference equal to 2n plus 1 lambda by 2. Let us see the theory of this Fresnel's biprism. Let us consider S1 and S2 are equidistant from S. S1 and S2 coherent sources are separated by a distance small d, and the screen is placed at a distance capital T from S1 and S2, and the point C on the screen is equidistant from S1 and S2. Therefore, the path difference between two waves is 0. Thus, the point C is having a maximum intensity. And consider the point P at a distance x from C, and the waves reach at a point P from S1 and S2. Hence, we are having some path difference between S2P and S1P. So, therefore, we have to find the path difference. So, as PQ is equal to x minus d by 2, PR is equal to x plus d by 2, and the path difference BP minus AP. So, BP square minus AP square equal to d square plus x plus d by 2 whole square and minus d square plus x minus d by 2 whole square. Then after simplification, we get BP minus AP is equal to 2xt divided by BP plus AP. And if P is very nearer to C, then what happens? BP and AP are equal to D, that is the distance between the sources, coherent sources and the screen. Therefore, the path difference equal to x into small d divided by capital D. Say this is equation 1. This is the path difference that we get from S1 and S2, as S1P and S2P having a path difference x small d divided by capital D. And now let us equate this path difference for a constructive interference as well as for a destructive interference. For a constructive interference, we know that path difference equal to n lambda. So, therefore, x into small d divided by capital D is equal to n lambda, where n equal to 0, 1, 2, 3 and so on. Or x equal to n for a nth distance, that is xn equal to n lambda capital D divided by small d. This is the distance of a bright fringe from the point C. At n equal to 1, it is x1 equal to lambda d by 2, and n equal to 2, it is 2 lambda d by d, n equal to 3, it is 3 lambda d by d, and so on. Therefore, the distance between any two conjugative bright fringes, either x3 minus x2 or x2 minus x1, we get the same value, that is lambda d by d. Therefore, it is denoted with the path fringe width, the beta is equal to lambda capital D divided by small d. Say this is equation 3. And now let us equate the path difference that we occur is equate with the destructive interference condition, that is path difference equal to 2n plus 1 lambda by 2. Therefore, x d by capital D is equal to 2n plus 1 lambda by 2, where n equal to 0, 1, 2 and 3 and so on. Then we get xn is equal to 2n plus 1 lambda capital D divided by 2 into small d. Say this is equation 4. This is the distance of the dark fringe from the point C. At n equal to 0, 1, 2, 3, we get x0, x1, x2 and so on. Then we find the distance between the any two consecutive dark fringe is the same as that we occurred in for the bright fringe, that is a lambda into capital D divided by small d. Therefore, the distance between any two consecutive bright fringe or any two consecutive dark fringe is the same, that is the fringe width beta is equal to lambda into capital D divided by small d. Now, let us determine experimentally the wavelength of monochromatic light using a Fresnel's biprism. All the Fresnel biprism and the whole setup of the experiment is shown in the figure. The source, Fresnel biprism and the screen, and also it is required one convex lens to determine the small d. The wavelength of the light can be determined using the formula lambda is equal to beta d divided by capital D. So here beta is the fringe width and small d is the distance between two virtual sources, and the capital D is the distance between the biprism and the screen, and which can be easily measured through the optical bench, so which is having a one scale attached with it. So let us find the fringe width beta. When the bright and dark fringes are observed in the field of view of eyepiece, the vertical crosswire is made to coincide with the center of the one of the bright fringe. Then the position of the eyepiece is read on the scale, say that is x naught. Then the micrometer screw of the eyepiece is moved slowly, and the number of bright fringes, say n, that pass across the crosswire is to be counted. Then the position of the crosswire is again read, say that is a xn for n number of fringes passes, and then fringe width is given by beta is equal to xn minus x naught divided by n. In this way, we are going to calculate the fringe width in the Fresnel's biprism experiment, and then determine the distance between two virtual sources. It is a small d. So we need a one convex lens which is placed in between the Fresnel biprism and the screen. Now, a convex lens of a short focal length is placed between the slit and the eyepiece such that it is very nearer to the biprism and moved until magnified images of S1 and S2 on the eyepiece. We get then measure the distance between the magnified images, say that is D1. Then the lens is moved towards the eyepiece till we get a diminished images observed as shown in the figure. Again, the distance between the images are measured, say that is D2. Let us see through the figure. See, lens, the one position is say L1, another position is say L2. First, we keep the L1 nearer to the biprism and we get magnified images, say the distance between the magnified images, say D1, small D1. And then move the convex lens towards the eyepiece, then we get a diminished images and we measure the distance between diminished images, and that is small t2. So with respect to those positions, we must measure u and v for different two magnified image position and diminished image position. And finally, the magnification m is equal to v by u, and that is equal to d1 by d. Actually, d is a mean position, that is actual position between S1 and S2. And we get for diminished images, we get another equation, that is u by v is equal to d2 by d. Then just by taking the multiplication of these two, we get d is equal to square root of d1 d2. So after knowing the values of d1 and d2, we can easily calculate the distance between two virtual sources as d is equal to square root of d1 d2. So using beta, small d and capital D in the equation, lambda is equal to beta d by d, the wavelength can be easily calculated. Let us see a simple problem. In a biprism experiment, the eyepiece was placed at a distance of 120 centimeter from the source. The distance between the two virtual sources was found to be 0.075 centimeter. Find the wavelength of the light of the source if the eyepiece has to be moved through a distance of 1.888 centimeter for 20 fringes to cross the field of view. So here, what are the given things? Let us see. The distance, that is capital D is equal to 120 centimeter. So then you make it in a meter. Next, the virtual distance, virtual source distance, that is small d is equal to 0.075 centimeter. Then they have given the for a 20 fringes, that is they have given how much of the distance it is moved by the eyepiece. So that is 1.8 cc, 1.888 centimeter. So if you take the 1.888 divided by 20, we get the fringe width beta. So by knowing beta, small d, capital D, wavelength of the light can be easily calculated. Let us summarize with some multiple choice questions. Fringe width number 1. Fringe width in interference of a light is, there are 4 options. A depends upon the fringe order, independent of the fringe order, either A or B or none of the above. No doubt it is independent of the fringe order. Let us see the answer. The answer is B, independent of the fringe order. Next, the resultant intensity is maximum when the path difference is. The resultant intensity is maximum when the path difference is equal to 2n plus 1 lambda by 2. Okay, let us see. So the answer is C. And now, interference fringes with a width 1.5 mm formed on the screen placed 1.2 meter from two coherent sources separated by a distance 0.45 mm. Then the wavelength, so again the lambda is equal to beta d by d. Then you get the answer A, 562 into 10 raised to minus 7 meter. Then, to determine the distance d between the two virtual sources using a Fresnel biprism, the d1 and d2 are found by keeping the lens. We know that the magnified image by keeping nearer to the biprism, and diminished image nearer to the eyepiece. That's why the answer is B. That is, for magnified image nearer to biprism and for diminished image nearer to eyepiece. And then coherent sources for interference in Fresnel biprism experiment are virtual, real, both A and B, or neither A or B. So it is a virtual. Answer is A. So let us recap whatever we have learned. That is the theory of interference using a Fresnel biprism. There we have calculated the expression of the wavelengths, and also experimentally we have calculated the wavelength of the source using a Fresnel biprism method. So these are the few references that you can refer. Thank you.